Okay, here's the first lesson in our level 1 of the ECG course. Again, level 1, G-rated stuff. Various units in this course. We're going to start in with the fundamentals lesson. The fundamentals unit, which will have several different lessons in it. And the first one, this one, is the electrical conduction system lesson. Fundamental stuff, basic cardiac anatomy with the chambers, vessels, and then the electrical system kind of superimposed on that. So big idea landmarks here for you to know: the SA node, the AV node, what are the Purkinjes, where's the His bundle and bundle branches, that sort of thing. And we'll go over this quite a bit. Plus there's a companion printout, more or less a PDF of these slides. So you can go back and look at these in detail while you listen to this a second, third, or 25th time, if that helps you. So why do we even need an electrical conduction system? Well, the deal is that we don't want the atria and the ventricles to contract at the same time. We want the atria to contract, stretch those ventricles, and that's called the atrial kick, the Frank Starling mechanism. So you get a better pump out of the left ventricle if you can stretch it first. It's like rubber band. If you want to pull that rubber band back a little bit and let it go, you'll get some pop. But if you can stretch it back quite a bit, you can get quite a bit of pop, and that's what the atrial kick concept is. If the atria can stretch that ventricle, the ventricles will be able to pump stronger, harder. So the electrical conduction system keeps that timed up, keeps all those things in sync the way we want them. And so the Frank Starling mechanism, now take a peek at this graph and look at the stroke volume as it's plotted up there along the y-axis, the vertical axis. The stroke volume goes up as the ventricular volume goes up. The more volume you have in the ventricle, the more it is stretched, then the more stroke volume you get, up to a point. If you look at the curve there at the top, right as it starts to arch over, now there's a point at which we shouldn't fill that ventricle any further. But you really get a lot more stroke volume, a lot more pumping action if you can get that atria to kick and stretch that ventricle up to a point. So that's what we're trying to get done. And the electrical system, electrical conduction system in the heart helps us get that done. All right, so key structures: the sinus node or the SA node, sinoatrial node, the SA node. Sinus node located in the upper part of the right atrium. That generates the pulse most of the time. That is where the impulse originates. The SA node fires on its own between 60 and 100 times a minute, so just think 80 as a rough idea. And those impulses travel down the conduction system very rapidly, much more rapidly than they would go cell to cell to cell to cell. We want the impulse to go down the conduction system. So the SA node fires, the impulse is transmitted over to the left atrium on Bachman's bundle, a real fast track fiber, conducting fiber that's very high speed, and also through the internodal pathway. So both of the atria are supposed to contract almost at the same time, and very shortly after that sinus node fires. Then the impulse comes back and pauses in the AV node for a little bit to let those ventricles stretch. That's the deal. The atria is supposed to contract and stretch, kick, stretch those ventricles, and the way this happens is that there's a pause in the impulse. The impulse slows down and hangs out for a bit in the AV node and the AV junction. Then just south of the AV node, still in the junction, we have the bundle of His. And the bundle of His branches. It splits into the left bundle branch and the right bundle branch. And then we'll talk later on about how the left bundle also branches into an anterior and posterior division called a fascicle. But we'll get to that later. Anyway, the impulse starts in the SA node, travels rapidly to both atria, comes back to the AV node, and then makes it through that division, that barrier between the atria and the ventricles, and works its way down into the ventricles. The impulse ends up in the Purkinje fibers, which are buried in the ventricular muscle. So how does this all work? Is it all controlled? Well, the command and control center, of course, is the brain, and the brain is in charge of and takes command of the heart through both the parasympathetic and the sympathetic nervous system. So you can see the nerves coming off there, the vagus nerve and the sympathetic nerves. And kind of pay particular attention here to where the various wires hook in. The sympathetic nervous system can control the SA node and the AV node and the ventricles. The parasympathetic, on the other hand, only has innervation, only has control over the SA and the AV node. Here's a more schematic version of the same thing. Again, when you see vagus, that's in the darker color, parasympathetic. The parasympathetic system only has control of the SA and the AV. It would slow down the SA node, slow down conduction through the AV node. The parasympathetic, on the other hand, would stimulate, speed up the SA node's firing, speed up conduction through the AV node, and can also directly impact the ventricles. Key point for much later on when we're talking about what to do with problems and what medications will impact which system and this and that. So while it may not make much sense to you or matter to you right now, try to save this sort of information for good. Sympathetic is going to innervate AV, or the SA, AV, and the ventricles, everything. But parasympathetic does not innervate the ventricles. So why is it that when the impulse starts in the SA node, why doesn't the entire heart just get activated and contract almost immediately? Well, the deal is that there is insulation between the atria and the ventricles. The fibrous tissue that's supporting the valves between the atria and the ventricle, the fibrous tissue acts as an insulator so that that impulse is forced into through the conduction system. The impulse is forced to go through the AV node. We want the impulse to go through the AV node. The AV node is really important to us. It allows us to sync up the atria and the ventricles because the AV node slows the impulse, holds it for just a little bit, and it's protective. The AV node is protective of the ventricles. So if the atria are going crazy and fibrillating more or less, then their impulses in the atria are 300 or 400 or 500 times a minute. The ventricles aren't putting up with that. They don't operate like that. Ventricles don't like to go that fast. And the AV node protects the ventricles from atrial chaos. That'd be another thing to write down on your arm and probably not wash off and kind of hang on to for a while. Now I drew this red line in here on this diagram. This is the conduction system in a schematic, more or less. And that red line, doesn't exist physically, but it's to represent that insulating property of the fibrous tissue between the atria and the ventricles. And again, trying to get that impulse to travel through the atria and then come back together at the AV node. Slow down for a little bit, let those ventricles stretch, that Frank Starling mechanism, that atrial kick. And so the red line, again, is supposed to be pretty much symbolizing the insulation between the atria and the ventricles. Another little concept for you here is that the AV junction is an area. The AV node is contained within that area. When we start talking about junctional rhythms and nodal and infranodal and some other stuff down the road, this will matter to you. Again, it may not make much sense and you really don't know why we're asking to know this now, but it would be very helpful for you to understand that the AV junction is an area. I think of it as a county. The AV junction is the county. AV node is located inside AV junction county, kind of up in the north part of the county. So schematically, there you have the chambers of the heart with the electrical system superimposed on top of it. And I just wanted to point out the AV junction. The AV junction contains the AV node and then the main bundle of His before they start to branch off. Speaking of branching off, the bundle of His branches into the left bundle branch and the right bundle branch, as you see in the top picture there. Then the bottom pictures are pretty much equivalent, but I wanted to put them both in there. I like the one on the left because it clearly shows you the Purkinjes. It shows you the tiny fibers that are buried through the cardiac muscle in both ventricles, and that's where the impulse is actually ending, where it actually stimulates cardiac cells that will contract. So you have the AV node the bundle of His, which splits into the left bundle branch and the right bundle branch. The left then splits again into the left anterior fascicle, the left posterior fascicle, and there's actually a septal fascicle as well. We don't spend any time talking about that other than on this slide, because really there's research going on to determine if it really even matters, but no one has figured out that it matters yet. And so once it matters to Mrs. Smith, then we'll talk about it. But right now it's just pure trivia. Yes, technically we believe there are 3 fascicles, but really from this point on we're going to talk about it like there's just 2. And then here's a cross-section of cardiac tissue, cardiac muscle. And you can see the Purkinje fibers buried in that muscle. That's where the impulse ends. It starts in the SA node, goes to both atria, comes back through the AV node, into the bundle branches, and the end of the bundle branches become Purkinje fibers, and those are the wires that are buried deep in the cardiac muscle, and they actually stimulate that myocardium to contract. So that's, you know, basic anatomy and electrical mechanical sort of stuff in a summary. Here we have kind of a schematic diagram of the conduction system. Again, you see the SA node up in the upper part of the right atrium. You see the AV node there at the junction of the atria and the ventricles. AV node being part of the AV junction area. The bundle of His, and it splits, and on and on. And the numbers represent the timing. So if the impulse starts at the 0 mark, it's in the AV node sometime around 0.7, 0.1, something like that, seconds. And it hangs out there a little bit, and then a little bit meaning like 0.05 seconds. So we're talking about very, very fast times here, but that pause is significant, as you can see there, and then it rapidly moves down the 2 bundle branches into the Purkinjes, and the ventricles are being stimulated somewhere around a fifth of a second, 0.2, 0.21, 0.22, about a fifth of a second after the impulse originates in the SA node. I thought it was kind of a cool diagram. Maybe trivia to you, but I hope it makes and matters in some way. So again, kind of a summary here. You have the vessels and chambers of the heart with the electrical system superimposed on top of it. The electrical system's role is to synchronize the atria and the ventricles so that they don't contract simultaneously. The atria contract, they kick, they stretch the ventricle. That allows the ventricle to pump harder, just like a rubber band, Frank-Starling mechanism. The way this all happens is the electrical conduction system. Impulse starts in the SA node, travels rapidly over Bachmann's bundle to the left atrium. Impulse comes back together in the AV node and pauses there for a bit, allows the atrial kick. The reason it does that is that those are insulated through there between the atria and the ventricles. It's got to go through the conduction system. It's got to go through the AV node. We love the AV node. It's our friend because it protects the ventricles from atrial chaos, and it is the place where the slowing and holding of the impulse for just a bit is where that occurs, and allows the ventricles to contract when they're supposed to. So electrical conduction system creating some mechanical activity.